Welcome. Today we start the second part of the lecture on decision trees. In the last class we looked at the definition of a decision tree, and we also looked at an algorithm ID3 which helps in constructing a decision tree or inducing a decision tree given some training data. So today we will further consider the decision tree learning algorithm. The instructional objectives of today's lecture are as follows. The student will learn how to evaluate a learning algorithm in terms of the error in the training set obtained on the training set and the error obtained on the test set. The student will learn how overfitting takes place in decision trees and how overfitting can be detected and avoided. We will talk about different stopping criteria for decision tree building. We will look at two different pruning techniques for pruning of the decision tree. First, we will look at reduced error pruning, and then we will look at rule post pruning. We will discuss how a decision tree can be made to work with continuous valued attribute. We will also discuss how missing values are handled in training data where the data is incomplete. So, some attributes have missing values. So, before we start, let us review what a decision tree is and look at an example decision tree that we considered in the last class. So, look at this diagram. If you look at this figure, every node in the decision tree, the internal nodes in the decision tree, test the value of an attribute. In this decision tree, there are 4 internal nodes. This node looks at the attribute for test, this node for the attribute of dry, this node attribute hot, and this node attribute dry. Every leaf node corresponds to a classification. So, this and this correspond to yes values, and this and this correspond to no values. The branches that come out of an internal node correspond to the different values the attribute at its parent can take. Taste can take the values sweet, sour, and bitter. So, we have 3 branches from test. Hot can take the values yes or no. So, we have 2 branches from hot. We will now just review the algorithm ID3 once more. The ID3 is the simplest algorithm for learning decision trees. It was given by Quinlan in the machine learning community. This algorithm was developed in 1989 parallelly by Quinlan in the field of machine learning and in the field of statistics by Bryman et al. So, let us look back at ID3. In ID3, we start the input is a set of training examples S. We have a set of attributes ATT. We have a training example S, and Q is the attribute on which we are trying to classify the classify the data. Now, ID3, if the training example is empty, ID3 does not proceed further. It just returns a single node with a default class or with the value failure. If S is not empty, but all elements of S belong to the same class, that is, if S is homogeneous, we stop growing the tree and we label that leaf node with the class to which all the examples in S belong to. Thirdly, if S is empty, that is, there are no more attributes left for testing, then also we cannot grow the tree any further. In that case, if S is not empty, we label the leaf with the majority class of the different elements of S belong to. Okay. Otherwise, we carry on this loop. So, when does one stop growing the tree? We stop growing the tree when either S is homogeneous or when X is empty. We also stop if S is empty. And then otherwise, if these conditions are not satisfied, we choose the best attribute. We choose the best attribute A by looking at the examples S and the attributes left. And then we branch on that attribute and grow a decision tree recursively. Now, there are several practical issues that come up in developing a decision tree, some of which are not properly handled in the ID3 algorithm. Some of these issues are: number one, we have to choose an appropriate attribute selection measure. As we have seen, there are different techniques, there can be different techniques for selecting attributes. The one we have been talking about is using information gain and entropy. Secondly, we have to decide how deep to grow the decision tree. The ID3 algorithm that we discuss stops when either S is empty or X is empty or when S is homogeneous. But we might decide to stop growing the tree earlier based on other criteria. ID3 will also fail if we reach a situation where S is not empty, but S is not empty, or X is empty and S is not homogeneous. Okay. In such situations, ID3 will fail and we have to take care of these situations. Number three, we have looked at how to handle attributes which have a finite number of values. Either they have Boolean values, true, false, or they take nominal values. For example, taste takes the value sweet, sour and bitter. But what about attributes which take real values? In many cases, for many training sets, attributes will take real values. For example, the value of temperature, the value of height, the value of income. They cannot be put into a small number of classes. How do we handle continuous values? So, decision tree algorithm can be modified to handle continuous values. Fourthly, we want to handle training data with missing attribute values. Sometimes we get a data for which we do not get the values of all the features. Either they are corrupted by noise or the features could not be measured or they are unavailable. So, we need to often deal with missing attribute values. There are other issues which we will not talk about in this class. For example, sometimes attributes have differing costs. You see, in the decision tree, once we have a decision tree, when we apply the decision tree, we take the example and test with the root node of the decision tree. Then we follow the appropriate branch. So, trying to classify the example involves testing some of the attributes. Now, it could be testing certain attributes are cheaper, testing certain attributes are more expensive. Consider a medical diagnosis system. Each attribute can correspond to some tests which have to be carried out. Some tests are cheaper, some tests are more expensive. So, we would prefer to carry out tests which are cheaper. So, growing a decision tree under those conditions will also, apart from looking at the simplicity or small decision trees, it will also take into account the cost of the different tests. And in number 6, we want improved computational efficiency. So, we will talk about some of these issues in today's class, and these issues are dealt with in later versions of the decision tree algorithms. For example, the C4.5 algorithm, which was developed by Quinlan in 1993, and then there are other versions of the decision tree algorithm including C5.0, and then there is the CART algorithm. And there are numerous other versions of decision tree algorithms which take care of these issues and go beyond the basic decision tree algorithm or ID3. Now, before we discuss some of these issues, let us discuss the issue of noise, which we have not talked about so far. You see, when you get the training data, there can be, the data may not be pure. There can be noise in the data. The noise can come in because of the error in obtaining the data, or error in measuring the data, or error in processing the data. So, due to this error in measuring or obtaining the data acquisition process can give us noisy data. For example, if the color is actually white, it may appear to us as gray, and so on. Secondly, sometimes what happens is that we do not choose the feature set properly, and our data set includes many features which are actually irrelevant to the classification task. The values of these features do not affect the actual classification. So, such attributes actually introduce noise in the classification process. And because of these reasons, because of the presence of irrelevant attributes, or because of the error in measurement, we may get two examples which have exactly the same values of all the attributes, but they belong to different classes. You see, certain classification problems are by themselves noisy. If we are not able to look at all the, if we skip some of the relevant features, we might get two data sets which agree with all the features that we have selected, but have different classes. This can also happen if some data is noisy. So, in any case, there is a situation where our decision, no matter what decision tree or what classifier we construct, that classifier cannot achieve 100% accuracy on the training set, because the training set contains two examples which have identical values of the attributes for different classes. So, any classifier that you construct will assign the same class to these two instances, which will not be correct. Now, let us see how we would, let us review rather how we would estimate the accuracy of a classifier. So, as we have mentioned earlier, we have some data. Let us say we have the data D. We divide D into two sets, the training set train and the test set test. We train the classifier using the training set, and after we have learned the classifier, we apply it on the test set. Because the classifier was trained as learned on the train set, it may be likely that the classifier is fit, or has been overfitted to the training set. So, to get a better idea of the true accuracy of the classifier, we should look at some unseen examples. And in order to get unseen examples, we keep aside a portion of D to evaluate the classifier. And we have also discussed briefly in the previous class the issue of overfitting. Typically, when we learn a classifier, any classifier, what happens is that as we increase the complexity. For example, in decision tree, as we increase the decision tree size or as we grow more nodes, the training set accuracy increases. We start with a decision tree having a single node and we gradually add nodes. As we add nodes, usually the training set accuracy goes up. However, if we test the accuracy on the test set, we see that the test set accuracy initially goes up and then it can slowly come down. And this phenomenon is known as overfitting. And we notice that based on the test set, this is the point where the classifier has highest accuracy on the test set. So, this is the optimal tree size. Now, why does such overfitting occur? Such overfitting can occur because there could be some regularity which is discovered in the data. Because we have only finite amount of data, some regularity can be perceived in the data due to some random behavior of the irrelevant attributes. They can mislead us in thinking that there is a pattern, which, and by taking advantage of this pattern, our classifier can increase accuracy in the training set, but this pattern may be present, may be absent from the test set. So, the test set accuracy goes down. So, initially, when the attributes are selected initially near the root of the tree, the better attributes get selected initially. So, the attributes which are really highly predictive are already taken care of near the root of the decision tree. So, after we have looked at the more important attributes, then we look for other attributes to grow the tree, and then we try to include these attributes which have less predictive power, and many of them are actually noisy. So, the highly predictive attributes occur near the root of the decision tree, and they are able to capture the more general patterns. The less predictive attributes are added later, and they mostly try to capture, overfit the tree to statistical noise. Now, how do we overcome the effect of overfitting? There are two major approaches to take care of overfitting. Firstly, we can stop growing the decision tree before overfitting sort of kicks in and takes over the process. So, we have to be careful how long to grow the tree. We should not grow the tree in all cases till completion as ID3 prescribes. Rather, we might decide to stop growing the tree earlier. The second approach involves pruning. So, we grow the tree quite deep and then we eliminate some lower portions of the tree as a post-processing step. So, stopping the tree while growing and first growing the tree and then pruning, these are two approaches that are used to stop the phenomena of overfitting. Now, let us look at how overfitting can be avoided. A tree or indeed any classifier is said to overfit the data if we let this tree grow deep enough so that it captures aberrations in the data. It tries to fit in the aberrations in the data to get perfect fit, and this harms the predictive power on unseen examples. For example, look at this example here. Suppose there is a feature called humidity, and as we increase the size of, and there is another feature called size. Now, we have two types of two types of classes, the blue class and the green class. So, what happens is that in the decision tree classifies, separates the feature space into different classes. Now, in this class there are all blue except this green. Now, initially the decision tree gets this class, gets this node consisting of all these 6 examples, then it further classifies, divides this set to separate this lone green class. And it may be that this is overfitting the data, possibly this is just noise, but the tree is grown deeper to capture this noise. This is another example of data that could be classified as noise. So, the point is that if we treat this whole thing as blue, this thing as green, this as green and this is white, maybe we will get a tree which has better generalization power, which works better with unseen data. But trying to fit all these cases and get 0 error on the training set may give us a classifier which has lower accuracy on the test set. So, let us come to the formal definition of overfitting. We say that a hypothesis H overfits a data set D. So, capital H is the hypothesis space. We are trying to find a hypothesis small h which belongs to the hypothesis space. We say that a hypothesis small h overfits a data set D. If there is another hypothesis H prime, so H is the hypothesis that we have obtained, H prime is another hypothesis in the hypothesis space. Now, if there exists an H prime which has worse classification accuracy on the data set, but which has better actual classification accuracy, that is H has better accuracy than H prime on the current training set, but H does not work very well on unseen data, then we say that H has been overfitted. We can see the phenomenon of overfitting by inspecting the following curve. This curve is similar to the curve that we looked at earlier. As we have noted that the accuracy, we plot accuracy along the y axis. So, this is 0.5, this is 0.6, this is 0.7, 0.8, 0.9 and 1. So, these are the values of the accuracy. Now, we see that the accuracy on the training set keeps going up as the size of the tree increases, but the accuracy on the test data initially goes up and then it goes down. So, this illustrates the phenomena of overfitting. So, beyond this point, the decision tree has tried to overfit the data. What causes a hypothesis to overfit the data? As we have seen that it may be due to random errors or noise, or it can be due to coincidental patterns. So, random errors or noise happens when examples have incorrect class level or incorrect attribute values due to error in measurement. Secondly, there can be coincidental patterns. By chance, the examples may seem to have a pattern due to the small size of the training sample. If you take a large training sample, such patterns are unlikely to be present. But due to this phenomena of overfitting, there can be a strong performance degradation. So, we have to deal with the effect of overfitting for any learning algorithm that we inspect. So, as we mentioned, there are 2 ways of dealing with overfitting: stopping and pruning. The simplest solution to overfitting is stopping. So, we want to stop growing the tree before overfitting takes over. When should we stop to grow the tree? There could be several things that we can do. First of all, we can grow the tree. If you use ID3, we can keep growing the tree until we get a single data point. Single data point obviously has a single class and we cannot proceed any further. But instead of doing that, we can stop when the data contains examples which have identical values of x, that is the data, we have some data which agree with the values of all the other attributes, but they belong to different classes. In this case, we do not get a homogeneous class, ID3 will fail, but we have reached a leaf, we cannot grow this tree further. In those situations, what we do is we choose the majority class to label the node. So, in this node we have examples, all of which have the same features, but they have different classes. We take the majority class and label it as the class of that node. Now, if you want to handle overfitting, we have to do something different. We have to stop growing the tree even earlier. In order to do that, there are several techniques that we can employ. So, when we have a node, we mentioned that we find the entropy of the examples at this node, and then we consider for a particular attribute that we use at the node, we look at the children. So, S is the data set here, S has an entropy of S. Now, due to this attribute A, which takes values true and false, we get the data sets S1 and S2. S is partitioned into S1 and S2. We find the entropy of S1, entropy of S2, and find the average entropy, weighted average entropy of S1 and S2. Now, if it happens that the entropy of the data set is below some threshold, then we need not. So, we ideally stop when entropy of the data set is 0, that is, they are all homogeneous. But instead of doing that, we can stop when the entropy of the data set is low. So, we can select a threshold which is slightly more than 0, and we can stop growing the tree when the entropy is smaller than the threshold. Then we did not consider this division. Secondly, we can stop growing the tree when, oops, let me just erase this. We can stop growing the tree when number of elements in the data set is below a threshold. So, if our S contains only 3 or 4 data items, we do not want to keep dividing the tree. So, only if S is large, then only we consider growing the tree. So, we stop when S is small. So, when S is small, we stop. When entropy is low, we stop. And thirdly, we also stop when the best next split does not reduce the average entropy. So, the split does not reduce the average entropy. So, we have reached a point where splitting does not help in the short run. So, these are the 3 techniques which can be used to stop growing the tree. Instead of stopping when entropy is 0, that is, the data set is fully homogeneous, we stop when the data set has low entropy. Secondly, we stop when the size of the data set at that node is small. Thirdly, we stop when the best split does not reduce the entropy. However, we can see that the third situation is not always wise. There are certain functions for which, if we look at the immediate gain in information, that immediate gain is not there, but there can be further gain as we go below the tree. For example, if you consider the XOR function, suppose you are trying to find A XOR B. If you either split on A or split on B at the top level, the entropy does not reduce, the entropy remains the same. The entropy only reduces when you, after A, if you test on B, then entropy reduces, or after B, if you test A, after 2 levels, the entropy reduces. So, this is not a wise decision in many cases. Now, let us look at the second alternative, which is pruning. So, for pruning, what we do is, when we prune a tree, usually the error in the training set will go up. But why do we prune the tree? We prune the tree so that the error, the true error, should go down. So how do we test the true error? We test the error on the test set, or called the validation set. So we keep aside a validation set. We test, we grow the tree on the training set and then prune it and check it on the validation set. So this validation set is called the holdout set. Actually, this validation set is slightly different from the test set. The test set is used to test the final tree after pruning. We have another set called the holdout set or validation set, which we use for validating the pruning. So we separate the training data into two parts. Most of the training data is used to build the tree, and this holdout set or validation set is used to validate the accuracy. So for pruning, what we do is we grow tree as far as possible. Instead of stopping early, we grow the tree quite deep, and then after growing the tree, we prune the tree until it keeps performing better on the held out data. So idea behind pruning is that the portion of the tree that models general patterns should work well on the holdout set, but the portion of the tree that fits noise should not work well on the holdout set. So this is a schematic. So we have a data set D, we divide it into training and testing, or the holdout. And we will consider two different approaches to pruning: reduced error pruning and rule post pruning. First, we will talk about reduced error pruning. In reduced error pruning, so in pruning, what we do usually is that we grow the tree to learn the training data, and then after growing the tree, we remove certain portions of the tree. So we prune certain portions of the tree, and so we get this new pruned tree. This is a pruned tree that we get, and the expectation is that the pruned tree will not overfit the data. So reduced error pruning is one of the techniques for pruning of decision tree. In reduced error pruning, we first grow the tree and then we do the following. We consider all the internal nodes of the tree. For each node, we check if removing it gives us any advantage in accuracy. So we consider all internal nodes in the tree. For each internal node, we check if removing the node along with the subtree below the node and assigning the most common class to this node, whether that improves accuracy on the validation set. So we find out the improvement, find out those intermediate nodes for which there is an improvement in accuracy, and let n star be the node for which the increase in accuracy is maximum. We prune the tree below n star, and then we go back to 2 until we get a situation where none of the nodes can be pruned to give better accuracy. So this is the essence of the algorithm reduced error pruning. We consider all internal nodes. For each internal node, we check if there is an improvement in accuracy by removing the tree below the node and replacing it by the majority value. For all such nodes for which there is improvement, we choose the node with highest improvement, which is n star. If no node shows improvement, we stop. If n star shows highest improvement, positive improvement, then we prune below n star and we continue using this algorithm. So reduced error pruning can be illustrated by this diagram. So suppose this is the original tree. This is the original tree. It has 7 nodes, 3 internal nodes. Now we can So what are the possible trees that we can get after pruning? So if we prune below this node, we get this tree 1. If we prune below this node, we get this tree 2. If we prune below this node, we get this tree T3. Now T4 involves pruning both below 1 as well as below 2. So we will consider these 3 trees T1, T2 and T3 as possible candidates. We find out whether these trees, whether the accuracy on the holdout set is better than the accuracy of the original tree. Among them we find the tree which has the highest accuracy. Suppose T2 has the highest accuracy, which is better than the accuracy of T. Then we will choose this tree and then we will proceed. Suppose we prune below this node, and so we get this as the prune tree. So T prime is the prune tree. Now we will again consider pruning this tree further. We can prune below this node to get this tree T1. To get this tree T1. We can prune below this node to get this tree T2. Evaluate them for accuracy, take the one with highest accuracy, or if both of them have worse accuracy on the holdout set than T prime, we retain T prime. This is how reduced error pruning proceeds. So this process continues until there is no improvement in the validation set. So this can be illustrated by this curve. This is the size of the tree, and we find that the accuracy on the validation data is initially validation. As we reduce the size of the tree, we start with this tree where accuracy is this. As we prune, we see that initially the accuracy is going up and then the accuracy goes down. So we stop pruning the tree here. The disadvantages of reduced error pruning is that if the original data set is, reduced error pruning is a very good technique, but it cannot be used if the training data set is small. If the original data set is small, if we keep aside something for the validation set, the training data will be further reduced. Also, we have seen that cross validation can be used to take care of less amount of training data, but in general reduced error pruning is not very good when we do not have enough data. Now we will discuss the second pruning method for pruning of decision trees, which is called rule post pruning. Basic idea behind rule post pruning is that after you construct the decision tree, you dismantle the tree and write out equivalent set of rules that denote the decision tree. You see, a decision tree can be expressed as a disjunction of all the paths along which the class is a given class, let us say C. So we find all leaves which are labeled by C, and we take the disjunction of all these paths. For each path, the formula is the conjunction of all the attributes and the branch that was followed to get to this leaf. Now we can open out this tree in terms of each such path. So we can convert the decision tree into rules. So we can have a rules corresponding to the positive class as well as rules corresponding to a negative class. Together we have a set of rules. Now after we get the set of rules, we can prune the rules independently. So what we do is that we look at each rule and see if we can drop some conditions in the rule and achieve higher accuracy on the validation set. So we first unroll the tree and we write it in the terms of rules. We sort the rules according to the accuracy, and then we say that to use the rules, first we will use the most accurate rules, and then we will keep using the rules until we get a rule match, and then we will get a classification. So this is the idea of using a rule set get from a decision tree. Then we can prune each of these rules. So, as an example, let us look at this decision tree which has 3 internal nodes x1, x2 and x3 and 3 classes A which corresponds to x1 equal to 0 and x2 equal to 0 or x1 equal to 1 and x3 equal to 0. There is the class B which corresponds to x1 equal to 0 and x2 equal to 1. There is the class C which corresponds to x1 equal to 1 and x3 equal to 1. So, corresponding to this decision tree, we can write out the rules as not x1 and so not x1 and not x2 implies class A. Also, not x1 and x2 implies class B. x1 and not x3 is class A, x1 and x3 is class C. So, we get this set of rules. Now, after we get these 4 rules, we try to see if we can drop conditions from these rules and get more accurate classifier. For example, we can drop the condition not x2 from this set. So, not x1 implies class A. Not x1 and x2 we have not pruned. So, we prune this rule and we prune this rule. So, we drop the condition x1 from this rule and we drop this condition not x2 from this rule. We get this new set of rules which is smaller than the previous set of rules, and we evaluate the accuracy of this whole rule set on the holdout set. So, if this rule set has higher accuracy, we adopt this rule set. So, we drop conditions from a rule so that the resulting rule set has higher accuracy on the holdout set. You see, can you spot what is the essential difference between reduced error pruning and rule post pruning? You see, in reduced error pruning, we only prune the bottom portion. When we prune a node, we prune everything below that node. You see, that node, an intermediate node that we prune can be shared by different paths. So, when we prune the node, we prune it along all the paths. When we write out the decision tree in the form of a number of rules and we look at each rule individually, we can prune a variable. For example, we are pruning the variable x1 for this rule. So, we are dropping x1 from this rule, but we are not dropping x1 from the other rules. So, we can independently drop conditions from the different rules, and we can drop a condition at the top of a tree and not drop a condition at the bottom. In reduced error pruning, when we drop a node, we drop everything below that node. So, what are the advantages of rule post pruning? The language. So, this rule post, what we get, this language is more expressive than a decision tree. When we get an arbitrary set of rules, they cannot always be efficiently expressed using a decision tree. A decision tree can express a disjunction of rules. They can be expressed, but not very efficiently. So, when we get the set of rules, we cannot reconstruct the decision tree back from the rules. We want to use these rules. So, this language is very expressive. Rules are easy to interpret. Pruning, as we just noted, is more flexible when we use rule post pruning. And finally, in practical application, this method has been seen to have yielded high accuracy. Now, let us look back methods of validating the new tree that we get. So, the methods that we have looked at so far are by using a validation set. The training set and validation set approach this is what we have mainly covered in this class. There are two other methods which we will briefly mention. So, the first method that we have been following involves dividing the data set T into two sets, train and test. We build a decision tree using train and we test the prune tree using test. The second method uses a statistical, does not use a validation set. So, this method can be used even when you do not have enough data to keep aside a validation set. This second method uses usually a statistical test like the chi-square test. So, the chi-square test is an example statistical method that people use. There are other tests. So, in this method we use all the data sets for training, and then we use a statistical test to decide if we should expand the node or not. Suppose you have grown this tree and then you consider the tree statistically, is there any benefit in expanding this node? We will not deal with further in this thing. So, several statistical tests can be employed. The third method is slightly different. It uses an encoding scheme to capture the size of the tree and the errors made by the tree. So, we use something like the minimum description length principle. So, the basic idea is that we use all the data set D to construct the tree, and we use the encoding scheme to know when to stop growing the tree. So, this method is known as the MDL principle. In MDL principle, usually what we do is we say that the best tree that we want is the tree so that the size of the tree in bits plus the size to represent the misclassified example. So, this two size, sum of these two sizes should be minimum. So, among, or suppose you have a tree T which is larger in size, suppose it contains 10 nodes and it misclassifies, so not 10, let us say T uses 20 nodes and it misclassifies 4 examples, 4 misclassifications. Suppose T prime has 6 nodes and it has 6 misclassifications. So, which one would you prefer? So, in order to compare these two schemes, the MDL principle is used. So, you find out for any of these schemes what is the number of bits you need to represent both the tree as well as the misclassified examples, and you take of the different alternatives that you have, you select that classifier for which this is minimum. So, this is the MDL principle, which is also inspired by the Occam's razor principle, which we discussed in the last class. Now, let us look at a few more issues concerning decision trees. One thing that we mentioned is that so far we have looked at attributes which have either Boolean values or only fixed values, nominal values. Now, what to do when we have attributes that take continuous values? For example, suppose you take the attribute temperature. So, temperature can take different values. Now, what we do in this case is that we try to discretize the continuous attributes, and in order to do that we select a split. So, suppose we say temperature greater than 30, temperature less than equal to 30. So, we split the values of the temperature into two sets. So, in order to find out a good split, what we do is we order all the values of temperature in the training set, and we find out, so we have ordered all the values and we find out for each value whether we have positive classes or negative classes. So, we find that here there is a positive class, there is a positive class, there is a positive class, then these are all negative examples, these are all positive examples, these are all negative examples. So, these examples are negative, these examples are negative, whereas these examples are positive, these examples are positive. So, when we decide to discretize the attribute, we select these are the possible points where we wish to discretize the values. So, we only consider those cut points where there is a change of class. We choose the cut point that maximizes information gain. So, to review, what we do is really we order the data set in terms of the temperature values, and for each instance we note against the temperature value what is the classification. Now, when we discretize the attribute, we cut it on one point. At this point, if we cut this, we find the information gain with respect to this cut. So, temperature less than 99.0 will be on this side. So, T less than 99 is on this side, T greater than equal to 99 is on this side. And with respect to, so this amounts to getting a Boolean feature. With respect to this Boolean feature, we can find the information gain. So, we consider cutting at different points. So, we consider cutting at this point, T less than 97.6, T greater than 97.6, T less than 100, T greater than 100. So, we can consider cutting at each of these points and find out the point for which the gain in information is maximum. Secondly, we wish to handle cases where attribute values are missing from the data set. For example, we may have a data set for which the value of mass is missing. We have the other features, but the value of one of the features is missing. What we do in this case? There are several things that we can do. One possibility is to assign the most common value of that attribute in this node. Suppose mass is missing, we look at the other examples, we find out what is the most common value of mass in the other examples, we put that value in this example. Okay. That is one strategy. The second strategy is we look at only those examples which have the same class as the current example. Suppose the current example is n, it has a class x. We find all other examples which belong to class x. For those examples, we find which value of mass is most common. We use that value of mass in this example. That is the second strategy. A third possible strategy is we assign a probability to each value of the attribute. Suppose mass can take 3 different values, right, m1, m2 and m3. So, for each of these values of mass, we assign a probability, and this probability is based on the frequency of those values in node n. So, each fraction is propagated down the tree. Suppose we find in the examples the mass has a value of m1 with probability 0.7, m2 with probability 0.2, m3 with probability 0.1. We assign these values with this probability to the node n, and we use that in the decision tree algorithm. So, this is another example of a continuous attribute. We have temperature, we have the class that we are trying to learn is the plate tennis class. We have ordered temperature, sorted temperature in ascending order, 15 degree, 18 degree, 19 degree, 22 degree, 24 degree, 27 degree. And for each of these instances, we have written down the class. We see that these are the points where the temperature value changes. So, we will be taking one of these as the cut point. For example, if we take this as the cut point, then we will test if temperature is less than 18.5 degree. If we cut at this point, we will check if temperature is less than 24.5 degrees centigrade. For each of these, we will find the information gain and select the one with the higher information gain. So, with this we stop today's lecture. We stop with some questions. Question 1, given a training set which is noisy, how will you decide when to stop growing the tree? Question 2, we never test the same attribute twice along one path in a decision tree. Explain why. Question 3, if you have a continuous attribute, do you think you can test the same attribute twice on the same path? Question 4, given training data, is it always possible to obtain a tree which has zero error on the training set? With this, we stop today's lecture. Thank you.